Okay, so good evening, everyone. This is the fifth tutorial session for the NPTEL course on mechanism and robot kinematics. It's Krishna Chanavtar here, who is a PMRF TA for this course. Keeping in line with what we have, the pattern that we have been following along for all the tutorial sessions. In today's session, also we will have the weekly review, so to speak, of the contents that was taught in the lectures for week 4, and we'll be solving certain problems, of course, from the assignments. And then today I would like to start one special session on representation of angles, uh, which is a very crucial thing in we can rather call it even as um, so we can call it, say, representative of attitude. And we will be covering some of the most widely used concepts such as Euler angles, then quaternions, and rotation vectors. So these are some certain things that we'll start be covering in this course in the sessions. So these are something which is slightly deviating from what is being done in the classrooms for the lectures corresponding to this course. Right. So at first, let's just briefly go through what was discussed in week 4 of this course. So we start with the displacement analysis, isn't it? So that is what we have been talking about during this course. And so we have looked at displacement analysis of mechanisms, isn't it? Both open and closed mechanisms, right? So what we call as it's the constraint mechanisms. And also we have started with open chain robots, so to speak, isn't it? So we have talked about robots such as RPR and all such mechanisms. So from today, in the week 4 during this week 4, we would be talking about we'll be talking about 3 DOF. So far we have covered 2 DOF kinematic chains, right, which includes 2R RP. So from this session, in week 4, we'll be discussing about 3 DOF kinematic chains. And we'll be talking about 3R and RPR, right? So today let's start with let's start with 3R mechanism, right? So here we go. So let's start with 3R robots. And mind you, they are all open chain robots. Now the question comes, what are open chains? Open chains. So open chains are those, say, mechanisms in which one end is free. So say, so for 3R, the kinematic diagram would look something like this. You would have 3 R joints, and this is the end effector. Right, so this is the end effector, and we have 3R. So we have 3 revolute joints. This is the grounded link, and then we have 3 our joints here. So that is why we call it, and this is free. So this makes it open chain. Fine. So let's start with a typical, as we had mentioned that there are two steps in displacement analysis, two aspects. One is what we call as the forward kinematics. So forward kinematics is much like a mathematical expression, right? Given some input, it's much like a function, right? Give some input and then determine output. So that's how it is, forward kinematics. So we provide something through the actuator and just look at where the end effector will say move to, isn't it? And inverse kinematics, it's, as the phrase says, it's inverse in that we prescribe, say we have determined, okay, this is where our end effector will be, say this end effector has to be in certain configuration. So given the end effector, location as well as orientation, both location and say an orientation, what is the required actuator input? So this is what it is. Right. So coming back to our 3R open chain robot. So let me just draw a schematic. So say I'll just first draw the coordinate system. Origin is fixed at this revolute joint here. And this part is grounded. And say we have links. Right. So as we recall, we have 3R. So this is R, this is R, as well as this is R. So we have 3 links. And this link says, and this is our X and Y as usual, coordinates, axis, sorry. So this is say theta 1, and this is say theta 2. And theta 2 will always be with respect to this line here, this link. So it will be, this is theta 2. And again, as we extrapolate link number, say ground is of course link 1. So this is link 2 and link 3. So this will be link 3's as we extend it, or this link 4 makes an angle with respect to the link 3. And this is of course the end effector. Right. And corresponding the lengths are link 1 is L1, link 2 is L1, link 3 is L2, and link 4 is L3. Now say this end effector, right? It will say somewhere here. So it will have some location. What is the location? It is XE, YE. These are the X and Y coordinates. And right now we are only talking about planar robotics, right? And this will also be making certain angle with the horizontal direction. So this we call as phi. So then this is how we are. So this is the orientation of the end effector with respect to x-axis. And x and y are just the coordinates for the same. So now the goal is to determine the location. So what, given some input theta 1, theta 2, theta 3. So let's say we start with the problem that given theta 1, theta 2, theta 3, what is the expression for xe, ye, and phi? So the location and the orientation. Fine. So we start with, say, determine what are the coordinates of, what is the coordinate for xe, right? So xe, the way we would say is, say we have this link and one, and mind you that xe will be the projection of this and effector on the x-axis. So there's xe. And now when we look at this schematic clearly, then we find that xe would be the sum of these three contributions: first contribution, second, and the third contribution, right? So it's composed of three contributions, and all of which are projections of the links on the x-axis. So this projection here, it is the projection of link 2 on x-axis. And as we recall, since this makes an angle θ1 with respect to x-axis, the projection is L cos θ1. Now, for link 3, how much does it project on x-axis, right? For that, we need to find what angle does link 2 make with respect to the x-axis. And what we say is, the θ2 as is given here is the uh, is the angle made by link 2 with respect to link 1, right? So essentially, and recall that what we can do is, let's make a line parallel to x-axis, and this is some angle, and this angle from the transversal law, as you have learned in, say, high school years, right? Transversal laws dictates that this angle will be the same here as well. So it means this angle is also equal to θ1. So essentially, right? So this angle, these are just the corresponding transversal angle. So this is θ1. So effectively, link 2 makes an angle θ1 plus θ2 with respect. Link 3 makes an angle of θ1 plus θ2 with respect to x-axis, because of which the projection will be L2 into cos θ1 plus θ2, right? Now coming back here, since this is the angle now θ1 plus θ2, and here link 3 makes an angle of θ3 with respect to link 4 makes an angle θ3 with respect to the link 3 here. Because, and then again from the law of this transversal rule, right, that this angle will be θ1 plus θ2. And because of which the total angle made by L3 with respect to, total angle made by the link 4 here with respect to the x-axis is L3 into cosine, the projection will be θ1 plus θ2 plus θ3, right? And mind you, fortuitively, we were also able to obtain the expression for phi. So phi we are already able to obtain. So phi is θ1 plus θ2 plus θ3. Right? So this we got even before, say, just during the process, we are able to obtain the expression for phi. Now xc is equal to L1 cosine θ1 plus L2 cosine θ1 plus θ2 plus L3 cosine θ1 plus θ2 plus θ3. See? So that is how we have. Now let's go to determine the expression for L for the y component of this particular event effector, right? So let me just extend the y-axis so that we are able to clearly draw the projections. Fine. So now we start from link to what is the length of the projection made by L1. So again, in this case as well, you'll have This is our, so this will be our YE. Now again, the YE is composed of the projections of three projections of the links. So this will be projection because of link 2. This is projection due to link 3. This is due to link 4. So since we have already determined all the angles, right, made with respect to x-axis, now things are a little straightforward. So the projection of link 2 is L1 cosine theta 1. For link 3, it is L2 cosine theta 1 plus theta 2. And L3 is, and link 4 is L3 cosine theta 1 plus theta 2 plus theta 3. And so we have the end effector location, the y coordinate of the end effector is L1. Sorry, it should be sine. Yeah, sorry. The sine. This is the vertical projection, right? Yeah, so we have L1 sine theta 1 plus L2 sine theta 2 plus sine theta 1 plus theta 2 and L3 sine theta 1 plus theta 2 plus theta 3, right? So this is what we was in for right? So for inverse kinematics, we are given XC, YE, and phi. And we have to determine theta 1, theta 2, and theta 3. Right? And so at first, what we do is let me just copy this. So we start with, say, and as we know from before is that phi is equal to theta 1 plus theta 2 plus theta 3. So this is clearly known to us, right? So what we do is we can write XC as L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 plus L3 cosine phi, because that's what it is. The sum is known. And at the same time, let's just rearrange it as XE minus L3 cosine phi is equal to L1 . Right, so we can have for this one as L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2. And for now, let's call this as some capital X. Likewise, for YE is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2 plus L3 sine phi. And this we can rearrange as ye minus L3 sine phi is equal to L1 sine phi 1 theta 1 plus L2 sine theta 1 plus theta 2. And let's call this as y. Right? Now what we can see here is that x is equal to L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, which we can write as x minus L1 cosine theta 1 is equal to L2 cosine theta 1 plus theta 2. Likewise, y is equal to L1 sine theta 1 plus L2 sine theta 1 plus theta 2. This implies that y minus L1 sine theta 1 equal to L2 sine theta 1 plus theta 2. Right? And what we clearly see is that here xe is known, L3 is obviously known, and phi is also known. Because of which the terms, I mean the value, we have some definite value which is known on the left hand side and which is equated to x. So it means that x is known, right? Likewise, in this case, y is known, L3 is known, and phi is known, because of which capital Y is also known. And then what we are able to do is we are able to write this expression here and have x minus L1 cosine phi theta 1 is equal to this. Now what we'll do is let's eliminate theta 2. The reason we eliminate is so that we have an expression in just in terms of theta 1, right? So that is the overall goal of doing this, right? So given that we have x is equal to, x minus L1 cosine theta 1 is equal to L2 cosine theta 1 plus theta 2, and y minus L1 sine theta 1 is equal to L2 sine theta 1 plus theta 2. So what we can do is to eliminate this uh, theta 2 from these equations. So we need to eliminate. So what we will be doing is that let's use the trigonometric identity, which you know very well by now, is that sine square psi plus cosine square psi is equal to 1. So that's what we are going to use. For this, we need to will square and add both the equations, both the above equations. So it becomes x minus L1 cosine theta 1 squared plus y minus L1 sine theta 1 squared is equal to L2 squared cosine square theta 1 plus theta 2 plus sine square theta 1 plus theta 2. And this evaluates to 1. And then we are left with x squared minus 2L1x cosine theta 1 plus L1 square cosine square theta 1 plus likewise y square minus 2L1y sine theta 1 plus L1 square sine square theta 1 is equal to L2 squared. Now what we do is let's perform some reduction here. So we have x squared plus y square is equal to before that, let's have plus L1 square cosine square theta 1 plus sine square theta 1, that is just L1 square, right? Minus 2L1 x1, 2L1 x cosine theta 1 minus 2L1 y sine theta 1 is equal to L2 squared. So what we do is let's do some algebraic rearrangement. So what we can do is let's transfer these terms on the right and then just take a mirror image about the equal to symbol, which is essentially just inversing, putting right on left and left on right. Then what we have is 2L1 x. We can just write it as 2L1 y sine theta 1 plus 2L1 x cosine theta 1 equal to x squared plus y squared plus L1 squared then minus L2 squared and then divide throughout by 2L1, which gives us y sine theta 1 plus x cosine theta 1 is equal to x square plus y square plus L1 square minus L2 square divided by 2L1. And this we can write out in the form of a sine theta 1 plus b cosine theta 1 is equal to c, and which you know very well how to solve it from. This has been in discussion since week 1 of this course, right? So once we obtain theta 1 by all the solving, transforming it to some, say, in expressing sine theta 1 in terms of tan theta 1 by 2 and solving a quadratic equation in tan theta 1 by 2, then we get the value for theta 1, the expression for theta 1, right? So now once we have this, then what we'll do is we will use these equations here, these two equations, right? So we have this here. We obtain theta 1. Now our goal is determine the 2, right? And this comes by, say, we divide the second equation by the first. So we have tan theta 1 plus theta 2 is equal to y minus L1 sine theta 1 divided by x minus L1 cosine theta 1. So from here we get the expression for, we already know the value of theta 1, so we'll have theta 2 is equal to, right? So it will be, we first determine the A tan of the quantity on this right here, this goes here, and here theta 1 of theta 2, then we have theta 2 is equal to A tan equal to A tan of the quantity here. Sorry. So we have, this implies that theta 1 plus theta 2, right? So it will be theta 2 is equal to A tan minus theta 1. So that is how we determine. And of course, theta 3, for that we use that expression of theta 1 plus theta 2 is equal to phi. So this implies that theta 3 is equal to phi minus theta 1 plus theta 2. That's how we do. This is in fact the inverse kinematics of this problem, right? And likewise, there is one another case for RPR, for which the kinematic diagram, right? So RPR, we have this kinematic chain. So it consists of three joints, two revolute, and one prism joints, right? So in this case, let me draw the schematic for this problem here. So let's first have the coordinate system set. Fix the origin of this coordinate system to the first revolute joint. Have one kinematic link here. And we allow one prismatic joint here. And then we go something like this. So we have R, this is P, this is R again, we'll have R again, and this ends at the end effector. So we have, so this link is of length L1, this link is of L2, but yeah, as per the schematic during the class, we just consider the separation distance, so to speak, the extension, or the throw as we call it, right? So we'll be taking from this end of the link with length L1 to this revolute joint here is S, and S is also a variable. And for the angles, we'll have this angle as theta 1, and say here this will be theta 3. Right. So let's determine the end effector. So end effector will also again have a position xe, ye, and this will be with some angle, some angle, say. So this end effector will be making some angle phi with respect to the x-axis. Now again, coming back to our forward kinematics, Fk. So we have given the parameters are theta 1 and then theta 3 and also S. And what we need to determine, so determine xe, ye, comma, phi, right? So for this, what we do is we start with the end effector xe. Before that, let's look at what all things do we require here, right? So this is theta 1, fine. So our goal is to determine the x coordinate of this here. So this is what we are looking at. And this will be composed of three contributions. So one from this, there's the second contribution, and this will be the third contribution, right? So for this, it's clear, okay, L1 cosine theta 1. So this is clear, the first contribution. For the second contribution, we need some angles, right? Some intermediate angles. So what we do is, I'll just stick to the notations in the series here, right? So this will be theta 1, of course, from the transverse rule. And we call this angle from here to here as alpha, such that this angle becomes theta 1 minus alpha, which is of course negative. So we should better call it, say, alpha 1 minus theta 1, right? So what we have here is x, and then so this is this contribution is also done. So it will be s into cosine of alpha 1 minus theta 1. And we take a look at the third contribution, for which, so this is alpha 1. So this is alpha minus theta 1. So this angle will also be alpha 1 minus theta 1. Sorry, alpha minus theta 1. Right? So this is alpha minus theta 1. And when we have theta 3, so theta 3, and what we require is, we require how much does this link here makes an angle with respect to x-axis, which is this angle. So this angle, to have this angle, we require theta 3 minus of alpha minus theta 1. And this comes to be theta 3 plus theta 1 minus alpha. Right? So which means that the projection of this link on the x-axis is also, we have an expression for this as well, right? So let's start with XC. So we have, for XC now, we have been able to obtain the individual contributions. So XC is equal to L1 cosine theta 1 plus S, right? This the distance of the link, or so the part of the link of this prism, of this link with this prismatic joint here, from this end to this, the length is S into cosine of alpha minus theta 1 plus again L2 into cosine theta 3 plus theta 1 minus alpha. Now, fortuitively, what we are able to do is, again, that we are able to get the value of phi here. So phi is actually this angle. So I'll just use some different color. So this is the phi here. And we are able to obtain phi during the process itself. So here phi is theta 3 plus theta 1 minus alpha. Right? Okay. Now for YE, we will have similar, likewise, we'll have this vertical projection distance. So L1 sine theta 1 plus S into sine alpha minus, so actually from the convention, it is that this angle here, sorry, from the convention, this angle here is, it's in negatively oriented, right? I mean, it's in the clockwise sense. In sense clockwise sense, because of which we'll have to have sine of minus into alpha minus theta 1. Then we have plus L2 sine of theta 3 right, sine of theta 3 plus theta 1 minus alpha. Right, and then we have L1 sine theta 1 plus S into sine theta 1 minus alpha, L2 sine theta 3 plus theta 1 minus alpha. So this is done, the forward kinematics. For the inverse kinematics, I'm sure you'll be, again, I'll just give a basic outline of what is to be done here. So let me just copy this to the next slide. Mhm. So let's bring it here. Right, so the goal is here that we have been given. So we are given so we are given XE, YE, and of course phi, and then determine theta 1, theta 3, and S. Right? So again, since we have phi is equal to theta 3 plus theta 1 minus alpha, which means that this is phi here. So we'll again use the same strategy that we'll rewrite XC is equal to L1 cosine theta 1 plus S cosine alpha minus theta 1 plus L2 cosine phi E minus L2 cosine phi is equal to L1 cosine theta 1 plus S into cosine alpha minus theta 1, and likewise YE minus L2 sine phi is equal to L1 sine phi theta 1 plus S into sine theta 1 minus alpha. And mind you that yes, cosine of minus theta is the same as cosine theta, right? So we can just, to be consistent, we can write it as theta minus alpha, doesn't matter. This we can call as S, like X, and this as Y. And terms on the right, on the left, XC is known, L2 is known, theta phi is known. Likewise, Y is known, and phi is known, and L2 is known, because of which X and Y are known. Now, what we can do here is we can rearrange such that X minus L1 cosine theta 1 is equal to S into cosine phi minus alpha. Likewise, Y minus L1 sine theta 1 is equal to S into sine theta 1 minus alpha. From here, we divide the first by the second. Right? We divide the first equation by the second equation, isn't it? And what we get is an expression eventually of the form A into sine theta 1 plus B into cosine theta 1 is equal to C. Of course, that's how after rearrangement we get, right? So here, now determine theta 1. So once we have theta 1, then use P is equal to theta 3 plus theta 1 minus alpha. This implies that theta 3 is equal to phi plus alpha minus theta 1. So we have theta 1, we have theta 3, And alpha is again a construction, I mean, it's a parameter. It depends on how do we set this prismatic angle. If this say this line of action, say to speak, the sliding direction is perpendicular to link L1, then this in that case alpha is equal to 90 degrees. If not, then we'll have alpha as some other angle, but structurally it is known, right? It is known from the structure. So we have theta1, theta3 we have been able to obtain. Now for S, what we'll do is we will use the formula here. I mean, this Pythagoras theorem, so to speak. We have x1 into x1 minus L1 cosine theta squared plus y minus L1 sine theta 1 whole square is equal to S square, right? Just by summing, right? And then we have this expression for S as well. So that's how it is. Fine. Now let's just go to the other types of the what we call as the closed chain robots. So now closed chain robots are, yeah. So essentially what there is that the end effector is somehow not directly, I mean, it's being actuated by multiple, what do you call, multiple such mechanisms, isn't it? So we have, say, multiple closed chain mechanisms which eventually actuate the end effector. I know it's a mouthful, so let me what we so what we have is we have this. I'm just writing some generic figure, and then we have, say, okay, let me make it not say some structure, right? And then we have, say, this is being able to, you can roll it and such that you're looking at the direction here. Something like some arbitrary thing, right? So once you just bring this to closer to this hinges here, you'll find that this angle is changing. So when we do a kinematic diagram here, we will find that it's composed of one set of mechanism, which is this, another set of mechanism, which is this. This is so it means this and this are connected, and this has is connected, right? So you see, right? So just, or maybe instead of determining the angle theta here, why not have something of this type? So we have some, say it's some very hypothetical like, I mean, robot here. So we have something standing on this vertically, and because of which it's able to move up and down just by sliding this. Right? So this will be here the end effector. And it is being actuated by two different set of mechanisms. So this is mechanism 1 and this is mechanism 2. So that is what closed chain robots essentially are, right? This is a very hypothetical robot, so it has hardly any. I myself, I'm not aware of what purpose it can be used for, but say there's just some thought experiment here. So ideally, this closed chain robots are always parallel manipulators. And you could see even here that both these mechanisms, I mean, the motion of mechanism 1 and mechanism 2 eventually lead to the action due to the end effector. Now you see how clear the things are here, right? And so by design, they are always parallel manipulators, and all actuators connected parallelly to the end effector. And you can see clearly here as well. So this is what closed chain robots essentially are. Right. So in the class we discussed, professor had discussed about he had mentioned about kinematic chains of the type kinematic chains of the type 2R, 3R, right? This is one such kinematic chain, and then we have RP, RPR, as well as 2R, RPR. Then we talked at length about 2R hyphen RPR. So here, this closed chain planar robots will constitutes of two such kinematic chains, right? Two kinematic chains. One is 2R, and the second kinematic chain is RPR. Schematically, the way we draw for the schematically, this closed chain robot would look like that. We have, say, origin centered here. Now, this is one segment or one part of this robot. So you can clearly see that this is, you have one R and second R, right? And this is the ground end, of course. So you have one R, two R, and here is the end effector. Ideally, this would have been the case if, say, we were dealing with only 2R planar robot. But here we are using some additional one more kinematic chain to be able to actuate it in say much more complicated ways. For this, what we do is we attach another kinematic chain of this type. This here. Now you'll ask, okay, but where it is used? So this particular kinematic chain, this particular planar robot is used in excavator. So there is an example like all that soil excavator, right? So for that, we are able to use it. Now in this case, so we have this kinematic chain, and this is the another kinematic chain. So that is why we call it's a set of two kinematic chains, and both are parallel in terms of kinematic diagrams, and both are eventually linked to the end effector, right? Which is at the terminal of this of the of both the manipulators. I mean both these kinematic chains here. So we have P, Q. These are the say the locations of these two hinge revolute joints, and you have this L1, and this is say A, B, E is the end effector. The distances are L3, the length is L3, and D is from here to here, right? And then we have S4 here. Prismatic will only move, say, along the length of along the length of the link itself, and we have L2 here. So for forward kinematics, of course, I won't be deriving completely here. We have given, what all do we need? So given theta, this and this, so these are the two actuators, theta and S4. And this will be determined, the numbers will be determined from the degree of freedom formula that we had, degree of freedom formula, right? From there, we can determine how many degrees of freedom we require. And then that helps us in also getting which two degrees of freedom we can have physically. I mean, that's just another thing here. And output is, so output what we have is X, E, and Y. So this is for the forward kinematics part. For the inverse kinematics part, it just goes the other way around, right? We have given X, E, Y, E, determine theta S4. So that is for the inverse approach. Fine. Okay. So let's briefly discuss also about the other mechanism that, I mean, the planar robot that was talked about, which is say 3 RPR. So in this case, so DOF will be equal to 3 DOF 3, and then there is another set of closed closed chain planar robot, right? Again, for which we have two types, say 3 into 3R, and which was discussed during the class, 3 into RPR. The kinematic diagrams for say 3 RPR, or maybe we can start with 3R. So in this case here, it implies that we have 3 into 3R. So that is what it means. So you have robots of with say 3 revolute joints, and they are all say assembled together to have one single robot chain, right? Single robot. So the goal is to have, say, the way we can so we can have, say, so say some big body connecting here. So this is the one we're talking about. So the kinematic chain is this one kinematic chain. Sorry, again. Sorry. We're a big body. So the kinematic chain here is, this is 1 3R, first, second, third, and this is the second 3R, and this is the third 3R, right, which is connected. So this is an example of 3R planar robots, right? And it has a degree of freedom 3. Likewise, for 3PR, one such example given talked about during the lecture was, so we here, of course, every kinematic chain will be of the form of RPR. So we have R, we have P, and eventually R. Likewise, R we have P and R, right? right? And one more hinge here, some connecting somewhere here. So there's also RP, right? So we have one chain RPR, second chain RPR, and third chain RPR. And then the factor is of course here, which makes an angle, some phi with respect to the x-axis. Likewise, here also we'll have all those forward kinematics and inverse kinematics approach going on. Fine. Right. So now what we do is, as we mentioned, that from today, let's also talk about some spatial sections that we'll usually have for, for the upcoming 2 or 3 sessions. So we'll be talking about spatial section is on representing attitude. It will contain about Euler angles. Then we have quaternions and rotation vectors. So for this program, I mean, for this sessions, I'll be following a write-up of the same name with the same title and authored by Professor James Dybel, Stanford. So he has authored this very condensed and compact set of, say, very much like a booklet on this topic, because this is often a topic which confuses lot many people in working in the area of robotics. And it's and also for people who are dealing with, say, rigid body dynamics and all, right? So it's a very useful thing to know about. So this is a lecture series you'll find online if you type this name. So the exact name is Euler angles, then unit quaternions. So let me write it in a more clear way, right? Okay, so representing attitude, Euler angles, right? And then we have unit quaternions and rotation vectors. And so and this you'll find it online anywhere. It's a very So let's start, at least for today. We'll just begin this monograph, set the stage so that we can just build upon in the future tutorial sessions. So fundamentally, we start with what do we mean by coordinate system, right? What are coordinate systems and why do we need it? So at first, need, right? Why do we need a coordinate system? The very need of coordinate system is to be able to quantitatively specify the location and orientation. So I think these are the two words I have been using frequently here of any body. So this is the need actually. So if we are able to have one such quantitative measure, quantitative say values using which we can define the location and the way it's oriented of any body, it really helps to say build say the mathematical formulation, build systems as well, right? And it's again very useful for us, right? So that is the basic need of why we want a coordinate system and what we need, what is required to define a coordinate system. Of course, first is consensus. So if you are dealing with large scale coordinate systems, say when we deal with systems like GPS and all, then of course a consensus has to be made on because that is obviously required. But say let's just it's something not of quantitative interest right now. So, but what all is required for to build a coordinate system? We require set of axes, and it should be, of course, three in number, and an origin. And this three number, we preferably orthogonal. So orthogonality really helps to simplify many of the, uh, it simplifies lot many things. When we say define the projections and all, it really helps if the axes are orthogonal in nature. So that is from mathematical point of view. From physical point of view, it must be inertial. Means either stationary or uniform or a constant. Either the origin should be stationary, that's what I mean here, or the coordinate system has to be stationary, or it should move with uniform velocity. Not uniform, it's constant, right? So essentially, it's any frame where we don't feel any force. So that is what inertial frame actually is. Say if we are on that frame and traveling along in the frame, then we do not feel any force. Then that is an inertial frame. So that is what is required for coordinate systems. We need set of three axes and an origin. This is the basic requirement. So oftentimes you will find that people will donate this as denote this any coordinate system as O, which means origin, and some coordinates EX, EY, and EZ. If we are dealing with coordinate system, I mean, if Cartesian coordinate system, then. So once we have, then we can talk about, we all at any point we deal with at least fundamentally, we deal with two coordinate systems. One, what we call as the world coordinate system. So the second point about being inertial applies for the world coordinate system. So world coordinate system must be an inertial space, or must be fixed in inertial space. Right? And we denote the origin, the world coordinate system, as x omega w. W implies world. So W implies that origin of the world coordinate system is denoted with x w. The second coordinate system is the most fundamental building block, right? When we are referring to one coordinate system to the other, is what we call as the body coordinate system or body fixed coordinate system. This is when a coordinate system is rigidly attached to the object whose attitude we want to describe. Attitude is essentially, attitude is the orientation, right? In this case, the origin we denote as x b, right? So this is, the origin is denoted with x vector and b. And mind you, this is also in terms of world coordinate system. That is how it is. Now, some of the conventions, some of the conventions that we would like to follow. If x vector is a point in world coordinates, then its corresponding, then x prime is the same point in body coordinates. So this means we use prime to determine whether any body is in coordinates, whether that point is expressed in body fitted body fitted or body fixed coordinates or not. Right? So which means that x vector 0, as we determine, it's just equivalent to, or it's just origin for the world coordinate system. Likewise, for the body fixed coordinate system, xb prime is equal to 0 for body. And this is for world. Right? So as we mentioned here in the previous slide here about the coordinate system, this xb is expressed in terms of world coordinate system, which means that xb need not be 0. However, when xb is defined in terms of the body coordinate system, the origin of the body coordinate system is defined in terms of body coordinate system, then it is an origin, which is prime. Right? So this is the convention we'll be using, or that has been used in this small monograph by Professor James here. Right? Now let's talk about rotation matrix. Let's talk about rotation matrix. So what is a rotation matrix? We often denote by R. And I'll just use double lines below it to denote that it's a second order tensor. So rotation matrix is a matrix when multiplied by a vector rotates the vector while preserving its length. So you have say this vector, right? So this is a vector here, some u vector. When we say multiply, when we say apply R vector R on this R matrix, then it will lead to some vector V. Some vector V here, such that the length of U vector is the same as V vector. So if it was a unit length, say if the length was unity for the vector U, the vector V will also have the same length. So that is what a rotation matrix does when applied to any vector, right? From mathematical point of view, in term like from this what is often called as the group theory, right? So the rotation matrix belongs to a class of operators or class of group which are called as SO3, which implies that it is special orthogonal group of 3 cross 3 matrices. That is what 3 implies here. Since it belongs to SO3 group, R has certain properties. The first property is that R, the determinant is plus minus 1, and its inverse is its transpose. I'll just note it down carefully here. R transpose is equal to R inverse, or vice versa. But rather better to call it R inverse is R transpose. Now, the rotation matrices for which R is equal to 1, for which determinant of R is equal to 1 is called proper rotation matrix. And when determinant of R is equal to minus 1, it is called as, of course, improper rotation matrix. They are also known as roto inversions, in the sense that it's composed of, it first rotates and then inverts. Inverts means some mirror operation. That's why it's called as roto inversions. All the time when we study the rigid body, we always only deal with proper rotation matrix is used for rigid body dynamics. Right? Then R rotation matrix is expressed as, it consists of three vectors, R1, R2, and R3, all of which have three components, right? So in a matrix, in this component form, we'll write it as R11, R21, R31, likewise R12, R22, R32, likewise R13, R23, and R33. So this is the representation in. So here what we see is that right. So we have this, these are the components R11, R12, R13, R21, R23, and the rest. So today, I think we'll call it an end here itself. In the next session, we will be starting with coordinate transformations. Or let's just do it today itself. So in coordinate transformation, what we do is we use rotation matrix to transform from say coordinates from one coordinate system to the other. Which means that say we have Z vector is an element of R3 and it is expressed as a point, or maybe it's a say vector in world coordinates. And then we have Z prime. It also is an element of R3 space, is a vector in body fixed coordinates. Then we have a relation between them, which is Z prime is equal to R into Z vector. And again, what we can have is Z vector is equal to R inverse of Z prime, which is, as we learned from the property, R inverse is R transpose into Z. So this is how we move from the representation in one coordinate frame to the other. Right? This is for a vector. That's how we do. And then, so this we have just started with coordinates. From in the next session, what we'll deal with is we'll talk about transformation matrix. And pose of a rigid body. I'll just be religiously following these notes. Then also talking about coordinate rotations. And then talk about direction cosine matrix. what is called as DCM properly in the literature, and also talk about basis vectors and we'll talk about rotation matrix multiplication. So these are some of the topics that we'll discuss in the next session. And if possible, we'll also try to talk about kinematics, and I will try to spend, say, more than an hour on this so that I'll be focusing less on module 3, module 5 lectures, and more on these topics here, more than an hour. Because this is often very useful if someone wants to pursue, say, interest, or say try to go deep into robotics, then these are something which we must be very clear about. Right. And about the angle representations, we'd be talking about Euler angles, rotation matrices, right? And about the Euler angle sequences, and then how they are linked to quaternions, the multiplication of quaternions, how they are linked to angular velocity, then about rotation angle, rotation vector multiplication. So these are all the topics that we'll be covering, and it will be very intensive. So I would like that please do download these notes from any online resource. Right. So representing attitude. And yeah, you can download it from, say, from the internet. Just type this exact title, and the first link would give you these notes. And please do read through it if you are able to. Yeah, I think with this we are done for the session today. And if you have any doubts, please do get back to me during the next session. And yes, yeah, I'll just stop recording.